Hello everybody, welcome to the fourth review session of this E7 MATLAB class. So we are starting the last week of the MATLAB class, so hopefully you'll see that you learned a lot in this class. So today we'll review the 4 of the modules, so the modules on polytopes and linear programming, the module on nonlinear algebraic equations, the numerical integration and differentiation, and the ordinary differential equations. So we'll review the few concepts that you learned in each of the modules, and hopefully this will help you have a more clear idea of what you saw. So let's start with the polytopes and linear programming. So the typical problem in linear programming is that you'll have to minimize a linear function that has linear inequality constraints. And you saw that this problem can be written in a matrix form. So you want to minimize a function of x that you can write as vector C transpose times x with the linear constraints a times x smaller than b. So A is an n by m matrix containing the coefficients of the linear constraints. B is n by 1 vector that contains the upper thresholds for the linear constraints. C is a m by 1 vector, and C contains the coefficients of the linear function to minimize. So because the function is a linear function of x, you can write this function as a vector C times x. And x is really the unknown, so it's an n by 1 vector that you want to find, and x contains the decision variables. So in these problems, you can define a, b, and c, and x is the unknown of the problem that you want to solve for. So make sure that you know the definitions of this of linear programming. So make sure you know what decision variables are, what the optimization criteria is. So here the optimization criteria is that you want to minimize the function. So the optimization criteria is the red part, so minimize C transpose times x. And the linear constraints are is corresponding to the inequality a times x smaller than b. So you saw in the module that these types of problems can be solved using the LP solver function. And you call the LP solver using the arguments C, A, and B in this order. And the first output argument of LP solver is x opt, so it's the solution of the problem we want. So x is equal to x opt is the optimal solution for x. And you have also two other arguments, so lambda containing the derivatives of the optimal cost x, and status corresponding to a character, a string, sorry, and it is equal to optimal when the optimization problem has been solved. So as an example, you saw the diet problem where you had to minimize the price of food with nutrient requirement constraints. So here the decision variables was corresponding to a vector containing for each food the amount of food to eat or to buy. And then the requirements for this problem was that you wanted the sum of the nutrition values times food amounts to be bigger than the thresholds, so to be sure that you have the correct amount of nutrients each day. And another requirement is that you want to buy positive amounts of food, of course. And the optimization criteria here is that you want to minimize the sum of costs times the food amounts. So then you had to define A, B, and C. So you have M types of food and N nutrients. So A was a matrix of size n plus m by m, containing the vertical concatenation of two matrices. So the first matrices contains the negative of the nutrition facts for each type of food. So here you wanted to make sure that the amount of nutrients you had for each type of nutrient was bigger than the thresholds contained in B. So remember that one of the trick here was to multiply A by minus 1 to make sure that you have the linear constraints in the correct order. So you wanted to have the nutrition values bigger than the thresholds, so you multiplied the nutrient values and the threshold by minus 1 so as to have the linear constraint in the correct order. And then same thing, so you wanted the amount of food to be positive. So you multiply the identity matrix by minus 1 in A, and by comparing that to zeros in B, this will ensure that each of the amounts is positive. So B has the same number of rows as A, so n plus m, and it contains the concatenation of the negative of the minimal amounts of nutrients, so same thing because we wanted the nutrients to be bigger than the thresholds, and then zeros to ensure that you buy positive amounts of food. C is the m by 1 vector containing the price for each type of food. And this is the function you want to minimize. And X is the decision variable vector, and it contains the different amounts of food. And so you could resolve this problem by calling LP solver CAB. So for this module, make sure that you know how to define A, B, C, and X. So I repeated an example here to make sure that you remember how to do that. And make sure you know how to go from linear constraints with a greater or equal sign to a smaller or equal. Yeah, and that's all I wanted to say for this module. So let's move to the module on nonlinear algebraic equations. So in this module, you learned how to solve algebraic equations. And this is another word for basically you learned how to find roots of functions on a given interval. And you saw two methods to do that. You saw the bisection method and you saw the fixed point method. So I'll review both of them. So let's start by the bisection method. So in the bisection algorithm, you want to find the root of a function f on a given interval ab, and where the starting condition is that f of a times f of b is smaller than 0. So this means that f of a and f of b have different signs, and that the function somewhere crosses the x-axis between a and b. So using iteration, the way that you implement the bisection method is that you define the midpoints being equal to the average of a and b, and then so you stop the algorithm when a stopping criterion is met. So when the absolute value of f at the midpoint is smaller than the tolerance. So while this stopping criterion is not met, you define x mid to be the average of a and b plus 2, and then if fa and fy have different signs, sorry, so here I meant x mid. So if fa and fx mid have different signs, then you know that the solution will be somewhere between a and x mid, and you define b to be x mid. Otherwise, you want to search for the roots on the other intervals, so x mid b, and this time you define a to be x mid, and you end the while loop here. So at each time, the length of the interval will be divided by 2, and in the end you will find an x mid where the absolute value of f at location x mid is smaller than the tolerance. So this is how you implemented the bisection method using iteration. Using recursion now, the principle is the same, except that in the if-else statement, instead of defining b and a to be x mid, you are going to do recursive calls to either the bisection of a and x mid, or to the bisection on the interval defined by x mid and b. And so when you use recursion, there is no while loop. Sorry, so the while loop is the same. Okay, so let's move to the fixed point method. So the fixed point method is usually more efficient than the bisection. So same thing, you want to find the roots of a on a given interval AB. So the principle of the fixed point method is that you will rewrite f of x equals 0 as g of x equals x, so where you define g to be a new function, and you define the sequence xk by xk plus 1 is equal to j of xk. And then if this sequence has a limit xlim, then you know that xlim is equal to g of xlim, and this means that f of xlim is equal to 0, and so xlim is a root of f. So you saw an example of the fixed point method. You saw the classical Newton-Raphson method. So in this method, g of x was defined to be x minus f of x divided by the derivative of f at location x. And so when you define g of x that way, x of k plus 1 at each time step is the intersection of the tangent at point xk with the x-axis. So you can draw very easily the sequence of points on the basis of the function f. And this function have the property of showing very rapid convergence, but it works in the case when the derivative of f at location x lim is different than 0, because otherwise the algorithm is diverging. So when you are in the case where the derivative of f at location x lim is equal to 0, it is better to use the modified Newton-Raphson method. And so here the definition of J is slightly modified. Instead of dividing by f prime of x for each location x, you divide by f prime of x at location x0, so at the starting point. And this prevents your algorithm from diverging. So then you saw a few MATLAB functions. So basically one MATLAB function to resolve nonlinear algebraic equations. And this is the F0 function. So the F0 function implements an algorithm that is a mix of bisection and fixed points. And it has 3 arguments. The first argument is the function handle corresponding to the function that you want to find the root of. And then you provide the starting point of the sequence, and you provide also a tolerance to stop the algorithm. So now let's move to the numerical integration and differentiation module. So in this module, you learned how to estimate the integral of a function between 2 points. So if f is a function, the problem is that we want to estimate the integral on an interval ab. And you saw different methods for implementing numerical integration. So the first method that you saw is the trapezoid formula, where you approximate the integral on the interval AB by the area of the trapezoid defined by the points A0, so the point on the x-axis having the axis A, the point B0, and then the images of B and A by the function, so B FB and A FA. So you estimate the value of the integral by the area of this trapezoid. And the integral is then defined by so the width, the length of the interval, so b minus a, and then the fa plus fb divided by 2. So this is the area of the trapezoid. So this is when you have just when you approximate the integral on the interval ab just having h equals to b minus a. But you can also go for the composite formula, where you will define smaller intervals, and so then you can define the area of the trapezoid between A and A plus H, and then A plus H and A plus 2H, etc. And then, so when you calculate the integral value, this will give you a pattern of 1, 2, 2, 2, 2 until the end to 1. So you have a MATLAB function that can directly compute the trapezoid approximation for the integral, and this is the function trapz, and trapz takes two arguments, x and y, corresponding to the x values and y values. So then you also saw the Simpson rule to integrate functions. So this time you'll give different weights to the function, to the value of the function f. So you'll give weight 1 to f of a, weight 1 to f of b, and then weight 4 to the midpoint, so to f of a plus b divided by 2. And so the sum of the coefficients is 6, so therefore you divide b minus a by 6. So this Simpson formula happens to be exact for polynomial functions with a degree smaller or equal to 3. So this is a very nice property. And when you calculate the composite formula, so you do the summations on the interval AB with the length of the subintervals being equal to h. And then you get a pattern of 1, 4, 2, 4, 2, etc. until 2, 4, 1. So when you call in MATLAB the function integral, this computes the approximation of the integral using the Simpson formula. And this function takes 3 arguments: the function handle of the function you want to integrate, and then a and b, the two, so the beginning and the end of the integration interval. So remember that for both methods you can improve the efficiency of the implementation by passing the values of the function evaluations when using recursion, so that you don't evaluate the function at the same point several times. And also remember that you can implement adaptive length for the intervals, so that you don't divide the length of the interval when the stopping criterion is already met, so that on the whole interval AB you can adjust the length of the intervals, the subintervals, only at the places where it's necessary. So that was it for the integration. After that you saw quickly different definitions for the differentiation approximation. So you saw the definition of the forward difference. This is defined by for a time step h, for a step h, f of x plus h minus f of x divided by h. The backward difference is very similar, but you consider the f function at the location x and x minus h. And you also saw the definition of the center difference, where you evaluate the function at f of x plus h and f of x minus h. So this is the 3 definitions that you need to know for the differentiation approximation. So let's move on to the next module that I'm going to talk about today, and that is ordinary differential equations. So when you solve a differential equation, you solve for a function y. So the unknown is a function. And in the problems you saw, it is always possible to transform the differential equation into a first order differential equation, meaning that you have a relation between only the derivative of f and f, and you are not considering the highest orders. So to resolve a differential equation, you need to know the initial condition, so the value of a function at the point x0. And you also need to know the relationship between y and the derivative of y on the whole definition domain. And this is given to you by a function, a relation of the form y prime of x is equal to some function implying x and y of x. So for this module, I would say make sure that you know how to transform a second order into a first order ODE. So you can review the examples in the homework. So you did that maybe 2 or 3 times in the homework. So make sure you remember how to do that. And remember that two MATLAB functions to resolve ODEs. So the function ODE23 and ODE45. So these are two different implementations to solve an ODE. And these functions take 3 arguments. The first one corresponds to a function handle corresponding to the function f that gives the relationship between y prime and x and y. The second argument corresponds to xa and xb, so the interval when you want to solve your function, the ODE. And the last argument is the initial condition. And you also saw one method to approximate the solution of an ordinary differential equation, and this is the Euler's method. So in the Euler's method, you impose a step for x, and you know the initial condition. And at each step, you approximate the value of the function by the value of the tangent. So to resolve an ODE with Euler's method, you are going to loop over the number of steps on the interval AB, and for each step, you are going to define y to be y plus f of yx, which is the derivative of y times dx. And you increment x to be x plus dx. So with Euler's method, at each time step, you estimate the value of the function by the value of the tangent at the new point. Okay, so that's what I wanted to say, and that's what I think it's important for you to know for the final when revising these modules. So I hope this will help you having clearer ideas. Good luck for your revisions, and I'll stop the recording here.